Okay, in this video what we're going to do is we're going to extend that example we talked about in the last video where we're trying to understand how we would determine the electric field due to a continuous charge distribution. That is, charge that is sort of continuously smeared across some object. So in this case what we're going to do is try to determine what the electric field is at some location relative to some rod or some line of charge where charge is continuously distributed across it uniformly. Now, what we're going to do in this setup is we're going to set up the problem, but we're not actually going to solve it because it turns out to be a pretty complicated problem to solve in general, but we want to talk about it in some detail anyway. So what we have here is a rod that is of length L, which is very long, and it has some charge Q that is uniformly distributed across it, which means that every chunk that is the same size has the same amount of charge in it. In particular, the chunk that we care about, little dx here, which is an infinitesimally thin chunk of charge, has an amount of charge dq. And what we talked about in the last video was that each of these chunks contributes a very small amount to the electric field, dE. So we can treat them as point charges, and we add them up, taking into account that each of them is at a different location, and in principle that each of them might have a different amount of charge. That's not the case for us because this is a uniformly distributed situation. So what we'll do is we'll introduce this concept of a charge density, which is how much charge is distributed per unit length, area, or volume. In our case, because this is a very thin, long rod, we're going to deal with what we will call a linear charge density, which I'll abbreviate as CD. And we often see described as lambda, in a sense to remind you that it is linear, right? Now, in this case, because it's uniformly distributed, it's simply taking the total amount of charge and distributed along the length L. That's how much the linear charge density would be. In the notes, what you'll see is a description of area densities and volume densities for charge, and those essentially replace the length here with areas and volumes and describe it sort of a different situation in terms of charge distributions, but it's still quite similar. So what we want to do is figure out how much total charge is sitting in this little dx, right? So if lambda is the charge density and dx is the length of that little chunk, then the total amount of charge sitting in there, little dq, is just lambda dx. So we have a description for lambda in terms of quantities that we know, which is q over L. So the charge that's sitting in that little bit of, that little chunk is q over L dx. So what that does for us is it helps us to specify, in terms of the electric field contributed by that chunk, something that is described in terms of a spatial variable, that is a variable that is describing three-dimensional space. The reason that that's useful is because when we talked about adding up all of these dEs, we have to add up all the charge. But we don't really know how to do that in terms of thinking about the limit of the physical space that we're in. So by recasting dq in terms of a spatial variable dx, what we can do is now say, well, we can start at one end of the rod and go all the way to the other end and stop when we get to the end, and we've added up all the pieces. So what we're going to do is we're going to impose a coordinate system on this situation to be able to do that, because that will help us to describe the r and r hat, which come from this definition here. We need a coordinate system to do that. So what I'll do is I'll erase a little bit of this stuff, make it a little more concrete in terms of what we're doing. So we'll say we're starting at the origin, and the rod ends at length L. We have to locate the source with respect to the origin. So we have to draw a vector that points from the source, from the origin to the source. And this vector is going to be our source. And what we will do is we'll call it, it'll have a length x. Now the reason that it has a length x is because it can exist anywhere along this rod. So it's sort of an arbitrary location along the rod, and as we add up along the rod, we need to take into account exactly where along the rod this charge happens to be. Now, the next thing we need to do is we need to locate the observation location, move this down here, with respect to the origin. And so we need some dimensions on that. So we'll go ahead and put something in. So we'll say, okay, well, this is maybe a distance d from the center of the rod. And this length is maybe some distance we'll call a. from the end of the rod. It doesn't really matter what it is, it's just some set of distances that are describing where that observation location is. So what we have is an observation location that is located a distance a in the x direction and a distance d in the y direction and 0 in the z. And we have a source location that is in the x direction only at a location x, which is allowed to vary. So that tells us that the separation vector r, which is going to be the observation minus the source location always, is going to be equal to the vector, let's see, a minus x, comma d, comma 0, right? It's kind of gross, but what we can do is we can see where this is going to come into our calculation for dE. So what we'll have here is a magnitude associated with the separation vector, which is given by a minus x squared plus d squared square root, and a unit vector that is exactly equal to the vector itself, which is going to be a minus x, comma d, comma 0, over this magnitude that we just calculated, a minus x squared plus d squared square root. Now that looks pretty awful, and in fact it is, because what we've done is we've chosen an arbitrary location somewhere in space, and so we haven't really thought about the symmetry, the geometry of this problem in a way to pick a location that might be a little simpler to calculate, which is what we're going to do in the next video. But what I want to communicate in this is that if you look at this r hat vector, it has both an x and a y component, meaning that ultimately when we calculate dE vector, what we're going to end up with is something that has an x component, a y component, and no z component, which means we'll have to do two integrals to figure out each of these. And these integrals are going to be relatively complicated because of all the stuff that's downstairs here. So we can put them into Wolfram Alpha, we can use Mathematica or something to do that. What we've done in this video is really just set up this problem to be able to solve it. But we won't really be doing this in an arbitrary location. In the next video what we'll do is we'll choose a slightly better location, which is at the end here, and actually solve that all the way through to show what the electric field is and how we make sense of it.